In this short lecture, we will introduce random sampling, estimation, confidence regions, and hypothesis testing. To highlight these concepts, we'll consider sampling from a Bernoulli distribution. So if you're not familiar with the Bernoulli distribution, then please watch my other clip on the introduction to probability, where I highlight the key concepts of probability using a Bernoulli distribution. Today's lecture will first start off by motivating sampling for a Bernoulli distribution and the notion of a random sample. We'll then look at that we go out and collect some sample data, and we want to estimate what's the true mean. And for a Bernoulli distribution, the mean is just a probability that some event occurs. So we'll look at using the sample mean to estimate the population mean. We'll look at the properties of the sample mean when we have a random sample. We'll show it some biased and consistent, which is sometimes known as a weak law of large numbers. We'll then demonstrate the weak law of large numbers in a simulation. This just shows that the sample mean gets nearer and nearer to the population mean when we have a random sample. We'll then look at the distribution of the sample mean using the central limit theorem, and we'll highlight the central limit theorem in a simulation. We'll then use these results on the distribution of the sample mean, to form a confidence region. So we'll give a region where, with some probability, the true mean lies in this region. Related to this, we'll then set up the notion of a hypothesis test. How do we test that the true mean takes on some particular value? And we'll just focus in on a two-sided test here. And again, throughout this clip, it's just motivating and giving intuition for the key concepts, so we'll not go into too much technical detail. Suppose we wish to go about estimating the probability that an event occurs. For example, the probability that someone's employed. Well, this is just what's known as a Bernoulli random variable. The event occurs, they're employed, or it doesn't occur, they're not employed. Again, we can state a random variable. We can have that person I, xi equals 1, is equivalent to them being employed. And define xi equals 0 is when person I is not employed. Okay, so then what is the probability that person I is employed? Pi, the probability that a certain person is unemployed, is unknown to us. What this means is each person has some probability that they are employed or not. So each person's random variable is a Bernoulli distribution, namely where the probability that the event occurs, for example that they're employed, equals Pi. So the overall question of this lecture is, how do we go about using sample observations to estimate this unknown probability? Before we can start looking at methods with which we can estimate this unknown probability of an event occurs, we first need to set up what's known as random sampling, a key concept in statistics. So suppose a researcher goes out and they ask a number of people, n people, whether or not they're employed or not, or whether or not a certain event occurs. Well, capital X1 to Xn, these are all random variables. These are all the probability, these all govern the probability that a particular person will tell us that they're employed or not. We've already seen before that each person's distribution is a Bernoulli. Each person has a certain probability that they're employed or not, and this is unknown to us. This probability is unknown to us. So this is a random variable. From our perspective, xi could be 1, they're employed or not, and we don't know. We go out into the population and we collect actual data. So we ask n people whether they're employed or not. So we will observe a sample observation, and we use lowercase letters to refer to a sample observation. So we can think that our sample was drawn from this random variable here, from this sample random variable. Okay, so we can think if we went out and asked n people over and over again, that we may get a different response. And again, so we can think the x1 to xn are fixed, and they came from some distribution. So we need to make some assumptions on the properties of these sample variables. The crucial assumption first is that each person has the same probability that the event occurs. This is known as the assumption that the sample variables are identically distributed. That in our case, this would mean every single person has the same probability that they are employed or not. Again, this assumption may not hold, but it's obviously going to be beneficial. It'd be much easier if everyone's got the same probability that they're employed. It's going to be much easier to pin down estimating this unknown probability P. Another crucial assumption is that each of the x1 to xn are all independent of each other. And again, we often justify this by going out and asking people completely at random. So again, if you just went to census data and picked people completely at random, we shouldn't expect that whether or not person 1 is employed should affect whether or not person 2 is employed, and so on. These two assumptions together are known as the IID assumption, that the data are independent and identically distributed. Sometimes this is just called random sampling, that we've just asked people completely at random. So everybody's response is completely independent of everyone else's, and each person had the same probability before we asked them that the event occurred or not. And again, these are assumptions. It may or may not hold. We're going to assume IID, that the sample is IID from now on in, because this has some very beneficial properties when it comes to estimating this unknown probability P. So now we have our sample data, and we now wish to go about estimating the probability that the event occurred, say the probability someone's employed. So as a recap, remember for a Bernoulli distribution, X is Bernoulli with probability P. The average value of X, E of X, is equal to P. So again, see the earlier clip on this, which derived the properties of a Bernoulli random variable. We show the mean is X, P, and we show the variance of X is P, 1 minus P. So we'll take these results as given. So for a Bernoulli random variable, estimating the probability the event occurs P is just the same as estimating the mean of X. Okay, so now we need to estimate the mean of X, which in this case would be the probability the event occurred. So the obvious candidate would be to estimate the true population mean, that's unknown to us, by using the sample mean. So the sample mean is just defined as the average of all the x's together divided by n. So as n gets bigger and bigger and bigger, it makes sense that the sample mean, the average of x in our sample, should get near to the true population value of x as n gets bigger. So let's look at the properties then of the sample mean. So we put forward the sample mean as a candidate estimate of the population mean, and we now want to see what properties it has. Ideally, we want the sample mean to be as near as possible to the population mean. So under the IID assumption, the random sampling, we can show that the sample mean is unbiased. This just says that the average of our sample mean is the population mean. So what is the average of the sample mean? So again, remember the sample mean is a random variable. If we keep asking a different set of people whether they're employed or not again and again and again, we'll find a different sample mean, or a different proportion of, equivalently, a different proportion of people that tell us are employed. So the idea is if we keep asking n people over and over and over again, what will be the average of this sample mean? So ideally, we'd want this average to be the population mean. We want our sample mean to be, on average, around the true population mean. Well, how can we work this out? Plug in from above into here. Is 1 over n here. Then we can use the additivity property of the expectation operator. So the average of the sum is a sum of all the averages. So again, 1 over n comes outside because it's constant. So this follows by additivity here. Then finally by the identical assumption, each one of these means are the same. They're just all equal to E of X because we've assumed that they're all the same. So this just equals E of X, which in our case is P. Remember, for a Bernoulli random variable, the average value of X is just a probability the event occurs. So we can see under the identical assumption that each person's got the same probability that the event occurs. The sample mean, on average, will be centered around the true population mean. So finally then, we want to see, well, as the sample size gets bigger and bigger and bigger, does the sample mean get nearer and nearer and nearer to the true population? This is known as consistency. And to show this result, we need to show the variance of the sample mean goes to 0. So we're now going to prove this result, and we can see this implies the variance of x bar n goes towards 0. So if the variance goes towards 0 and the sample mean is on average near to the population mean, it's saying that x bar n is converging in probability to the true population mean P. Just means then, as n gets bigger and bigger and bigger, the variance of the sample mean is getting near to 0, and it's getting near, and it's centered around the population mean. So it must mean that the sample mean gets nearer and nearer and nearer to the true population mean. So how do we show this result? Well, we just plug in x bar n. Again, the 1 over n comes out squared. And again, remember the properties of the variance of the sum of n variables. N comes out squared. And we're going to use now the identical assumption. Under the assumption all the x's are identically distributed, then the variance of the sum is just a sum of all the variances because they're all uncorrelated with each other by the independence assumption. Then finally by the identical assumption, each one of these variances of xi is just equal to the variance of x. They're all constant. So we're going to get n times variance of x divided by n squared, which is just variance of x over n. So we've shown that the variance of the sample mean is converging to naught. So it means that the sample mean is getting nearer and nearer and nearer to a point. And we know that this point is the true sample mean, the true population mean, which is just p. So these two things together give us what's known as consistency, that as n gets bigger and bigger, the sample mean gets nearer and nearer and nearer in probability to the true population mean. And we're now going to highlight this result in a simulation. We now provide a demonstration of the weak law of large numbers. So the weak law of large numbers just shows that the sample mean is a consistent estimate of the population mean. Namely, as n gets bigger and bigger, the sample mean will converge nearer and nearer and nearer in probability to the true population mean when the data are IID. We do the following simulation. So we're going to simulate the distribution of the sample mean of a Bernoulli distribution. So we draw 300 samples, x1 to xn, from a Bernoulli distribution with probability half. So the event happens with probability half. So we use a random number generator. For each sample size n, we draw a set of sample observations from an IID Bernoulli random sample. We do this 300 times. Each time we calculate the mean and we plot the distribution of the sample mean for that sample size. So for example, take n equals 5. We draw 300 samples of size 5. For each sample, we calculate the mean of those 5 numbers, and we then plot the distribution in this graph here. And then we do this for n equals 1, 2, 3, 4, and 5. And what we will show is that the distribution of the sample mean gets nearer and nearer and nearer to a half. And again, because now the true population mean here is a half. Remember, for Bernoulli, the E of x, the average of x, is p, the probability of the event. So we can see this then, we now draw this out. You can see as n gets bigger and bigger and bigger, the distribution, the width of the distribution is getting nearer and nearer and nearer to a half. So what this is saying is an increasing probability that the sample mean is getting nearer and nearer and nearer to a half. But remember, half is the true population mean here. Okay. We'll now look at deriving the distribution of the sample mean using one of the most powerful results in statistics, the central limit theorem. The central limit theorem says if our sample is IID and the variance of x is finite, this statistic here will behave like a normal distribution as n gets bigger and bigger and bigger. What this says is this statistic will converge in distribution to a normal not 1, which just means that this statistic will be distributed like a normal, standard normal not 1 as n gets bigger and bigger and bigger. And this is very powerful because it doesn't matter what the form of the distribution of x is. In our case, we're considering the Bernoulli random variable, which is discrete, but it could be Poisson or exponential and so on. Doesn't matter what the distribution is of the actual sample data x, this transformed statistic here will behave like a normal not 1 distribution. This is very powerful then because it allows us to make probability statements about what is the true E of x, and which is now going to be the topic of the talk. How do we form confidence regions using this result, and how do we form hypothesis tests on what is the true mean of x using this result? Okay, so the next line just formally writes down what converging distribution means. It just means that this statistic, as n gets bigger and bigger, the probability that it lies in a certain range, plus or minus c, is just governed by the probability that a standard normal, z, which is just normal not 1, lies in the range c minus c. So this line just formalizes the line above. As n gets bigger and bigger, the probability that this statistic lies in a certain range is just equal to the probability that a standard normal lies in a certain range. For our example, we know that E of x is p for a Bernoulli, and the variance of x is 1 minus p. So we can plug these two things in. So again, in our Bernoulli case, this simplifies down to here. Then finally we can use an estimate of p. So we know then under IID that xn converges in probability to p, which just means from here to here, we can just replace the unknown p with an estimate of p. So all we've done is remove the true population mean, which is unknown to us, and we plugged in our best estimate. And we know as n gets bigger, the sample mean gets nearer and nearer to the true population mean, which is why we can go from the second line to the third. So we're going to use this result. This result is crucial when we want to start making hypotheses on what is the true value of p, which is going to be the topic of the final part of this lecture. But firstly, we'll highlight this result. In a simulation, we're going to show that the central limit theorem holds. We're going to show that the distribution of this statistic will behave like a normal as n gets bigger and bigger. We now provide a demonstration of the central limit theorem using our simulation example from the Bernoulli from earlier. So, well, again, we'll simulate from Bernoulli distribution, draw 300 samples, x1 to xn, from an IID Bernoulli sample with probability 1/2. So again, we use a random number generator. We generate a sample, we work out the mean, we do that 300 times, and we can plot the distribution then of the sample mean for that sample size. So, for example, n equals 5, we generate 300 samples, work out the sample mean in each case, then we construct this statistic here from the previous slide, and we show, as we've seen, by the central limit theorem, this should behave like a normal 0,1 as n gets bigger and bigger and bigger and bigger. So in the left-hand side, we plot the statistic as n gets bigger. So we can see then, in the graph at the first, for n equals 1, we can see this has got to be clear, the blue dotted line is the density function of a normal 0,1, and the red line is the best fit to the distribution of the statistic here for a particular n. So the red curve should coincide with the blue curve as n gets bigger and bigger. Again, the red curve is a distribution of the statistic for a particular sample size, and the blue curve is the distribution of a normal 0,1. The two things should coincide. So for sample size 1 then, we can see the distribution of the statistic is very obscure. And we can see it can only take two values, because we can see we have a draw from a Bernoulli distribution which can take values just 0 and 1. So the average of just one number from here, well, it has to be either a 0 or a 1. So this statistic can only take on two values when n equals 1. Because I said again, when n equals 1 from Bernoulli, the sample average is just the draw itself, and the draw can either be a 0 or a 1. This means that x bar 1 can only be 0 or a 1, which means the statistic can only take on two values, here -1 or 1. This is why we get this strange distribution here. We can then look at sample size 2, and again, the statistic can only take on three values now. And we can see the red curve is highly non-normal. So we can see that the approximation is that the distribution of the statistic for n equals 2 is nowhere near the normal 0,1. But as n gets bigger, we should find the distribution gets nearer and nearer and nearer. So again, n equals 3, the distribution of the statistic is the red line, very, very obscure. And again, n equals 4, it's starting to get better, but still obviously very far away from the blue normal curve. And again, we can now let the sample get bigger and bigger. We can see even at n equals 9, 10, the curve is quite off. But as the sample gets bigger, it gets nearer and nearer and nearer. The distribution of this for n equals large starts to become normal. And we can see it's starting to happen now. Sample size 20, 21, the red curve and the blue curve are almost overlapping, or they're getting nearer. And the approximations gets better and better, which demonstrates the central limit theorem. As n gets bigger, the distribution of the statistic for that particular sample size gets nearer and nearer to a normal 0,1. And we can see here that our sample, our x, is discrete, it's not continuous. So x, but the Bernoulli random variable could not be any further away from a normal distribution. But we're seeing that this sample average, this particular statistic, this transformation of the sample average becomes a normal 0,1. It's an extremely powerful result. We can use the results on the distribution of the sample mean, using the central limit theorem from before, to provide a region where the true unknown population mean will lie in this region with a certain probability. Okay. So we just restate the central limit theorem from before. We know that the statistic will lie in plus or minus c in some range with probability governed by a standard normal, where this plots the distribution of the standard normal. So again, as n gets bigger, that this statistic has the same distribution as a normal 0, 1. So we wish to get a range. We want to get a range where we can be sure that the unknown probability p lies in this range with a certain probability. So for example, we may find that with 95% probability p lies between, say, 1/3 and 2/3, for example. So this is obviously very useful for policy analysis, which allows us to make inferences on how large or small the probability is that the event occurs. Well, we can just use this result to rearrange. The idea is to rearrange this inequality now for p. Well, we can just, to simplify, define standard deviation as square root x bar n, just to simplify down. Well, we can divide both sides by square root n and multiply by the standard deviation. If we do this to both sides, we find this here, and we can then rearrange again. So all we've done is divide both sides by n and multiply by the standard deviation. Well, we can now rearrange for p. This inequality, well, we can first rearrange the right hand side. Well, we have x bar n minus p less than this here. So we can now get an inequality for p. Take p to the right hand side, we have p is greater than or equal to x bar n minus c over root n sd. And we can now rearrange the left hand side of this equation. We can now rearrange this one here. To both sides, add p to the left hand side and add. So take p over here and we will get, and take this term over, we can get p is less than or equal to x bar n plus c sd over square root of n. So this is it. These two together just give us that p is less than or equal to x bar n plus the standard c times standard deviation over root n, and it's greater than or equal to x bar n minus c standard deviation over root n. Well, all we've shown is that this inequality here is just equivalent to this inequality here. All we've done is to rearrange for p. So the probability that p lies in this range is given by a normal 0, 1. So we can choose this c governed by the standard normal distribution. So for example, again, if we see here, if we choose c equals 2, there's a 95% chance that z lies in this range. So it's c equals 2, then take c equals 2, then there's a 95% probability that p will lie in the range x bar n plus or minus 2 times standard deviation over square root of n. So all we do is we pick the size of our confidence region. What probability do we want the range to include p? 95 or 99%? So again, if you wanted a 99% range, we choose c equals 3, and so on. So again, we now know that the probability that p lies in this upper and lower bound is 95%, and we can form a confidence region. So we just saw the notion of a confidence region, which gives us a region where the true population mean lies in a certain range with a certain probability. We may want to look at just testing that the sample mean, the population mean, which in our case is the probability that the event occurs, takes on some particular value. For example, we may want to test the probability that someone's employed is, say, 0.2. Well, the null hypothesis is a hypothesis we wish to test. We wish to test that true unknown probability equals some hypothesized value, pH0. So for example, we may have the hypothesis that the event happens with probability half. And we want to test the likeliness that this null is true. And again, we then specify what's the alternative hypothesis. Well, that the null isn't true, that the true probability doesn't equal our hypothesized value. So how do you go about testing this particular null hypothesis? Well, again, we're going to use the central limit theorem. We're going to use the fact that this statistic is distributed as a normal not 1. This notation here, it just means that this statistic is approximately normally distributed. So it's just another way of saying the central limit theorem holds. As n gets bigger, this statistic should be near to a normal not 1, which is what we saw in the simulation earlier. So if the null is true, then this means the true probability, the true mean, is pH naught. So we can use this result. It tells us that population mean minus sample mean, time minus population mean times this divided by this. Well, under the null, this is distributed as a normal not 1. Because under the null, the true P is equal to pH naught. So all we've done is substitute this into here. So under the null, this random variable behaves like a normal not 1. Well, we have our sample draw from this particular distribution. We observe x bar n, our sample mean, which was drawn from the sample distribution of this variable here. So we can construct this statistic, sometimes known as a t statistic. So we can observe this statistic here. We can construct this statistic, and what we know is it came from this distribution here. This statistic was drawn from this distribution. Again, capital X is a random variable, little x is our particular sample observation. So we can think of, if we kept drawing this statistic again and again and again, if we kept drawing different sample sizes, size n, and plotted its distribution, the distribution of this, well, would be given by the distribution of this, which is a normal not 1, by the central limit theorem. Well, why is this useful then? Well, we can construct this statistic here. So if the null was true, we know this came from a normal not 1 distribution. Okay, well, this allows us to make a probability statement on the likeliness that the null is true. Say, for example, this statistic was 5. Then the probability that we'd observe a draw from a normal distribution of 5 is very, very small. We can see the probability of observing anything bigger than a 3 or minus 3 is less than 1%. It's very, very small for a normal not 1. So if the null was true, this sample draw came from a normal distribution, because again, under the null, this statistic behaves like a normal not 1, and we have some draw from this distribution. So this, we know this statistic on the left came from a normal not 1. So if it's too large, it's unlikely the null is true. So if the statistic is 3, 4, 5, it's saying that for the null to be true, there's an extremely small probability that we'd observe a statistic this large. So this is the idea behind an hypothesis test. So for the test, we want to then have an acceptance region where we think there's enough evidence that the null is true, i.e. that this statistic is near enough to not, it's not too large, and a rejection region where if this statistic crosses a certain threshold, there's a small probability the null is true, so we reject. So for example, we may want to pick a test where we will reject the null 5% of the time. So again, if we picked this would be our acceptance region here. So if we pick this as our acceptance region, so what this means is if this statistic, the t statistic, if it lied between plus or minus 2, then we're 95% sure the null is true. Because we know if the null was true, there's a 95% chance it would lie in this range. And then we would reject otherwise. We would reject if the statistic lied outside that range, because we would then be 5% or less sure that the null was true. So then we reject, so it's very simple then. We call this the t, call this t. We reject, we accept the null if t less than or equal to some critical value, call it c, and we reject otherwise. So if t is greater than c or t is less than minus c. This just says that it lies in the acceptance region. So for example, for c equals 2, we would get a 5% test. There's 95% chance it would lie in this range. And if t lied outside, plus or minus 2, then there's less than 5% chance that the null could have been true. So the idea of the test is we choose some cut-off point. We choose how sure we want to be that the null is true. So for example, we may do a 1% test. So that would be 99%. If we accept the null, we're 99% sure that the true unknown probability took on our hypothesized value.